All right, so the last talk of the session is on impredicative observational equality and is given by Loïc Pujet.
So hi everyone, and thank you for attending to my presentation. So today I will be talking about some joint work with Nicolas Tabareau, which is about impredicativity and observational equality. All right, so first let me take a few minutes to explain what impredicativity is all about. So, you know, it's like this sort of old-fashioned, slightly vague notion that has been around in mathematical logic since the early 20th century. And roughly, a definition is said to be impredicative when it involves a quantification over a set that contains the object that we are trying to define. And such definitions are like super frequent in mathematics. You can see here that I've reproduced a standard definition in group theory of a subgroup that is generated by a subset. And this definition involves a quantification over all of the subgroups of G to define a subgroup of G, which is, well, impredicative. In dependent type theory, the possibility to make such impredicative definitions is modeled by what we call impredicative sorts. So an impredicative sort is a sort that is closed under a dependent product indexed by arbitrary types. For instance, the sort prop of Coq propositions is impredicative. This is because, well, if you have a proposition B that depends on a type A, then the dependent product pi AB will be a proposition even if the type A happens to be like super large and even larger than the type of propositions. And compare this to the type hierarchy of Coq, which does not share the same properties. For the type hierarchy, if you have a type B that depends on another type A, then the sort of the dependent product pi AB will not only depend on the sort of B, but also on the sort of A. And if A happens to be larger than B, like in the sense that it leaves a universe higher, then the dependent product will leave a universe higher too. And for this reason, we call the type hierarchy predicative. Well, right, this is a definition. And it turns out that having an impredicative sort in your proof assistant is super useful because, well, for several reasons, and on a very down-to-earth practical level, it minimizes and simplifies dealing with universe levels because, well, we only have one impredicative sort instead of having a full hierarchy. So you do not have to care about like universe level problems. But if you do care, the precedent talk is a great way to deal with them, I guess. Another reason, more important, for which it is good to have impredicativity is, well, that it is actually necessary if you want to define many mathematical constructions. For instance, like if you want to define any non-trivial complete lattice, you will need impredicativity. And these things are involved in some like super important theorems, such as Tarski's fixed point theorem, which is like useful even for PL people, you know. And finally, some theorems that do not even talk about complex higher order objects end up being impossible to prove with only predicativity. And the most famous example in our community is surely normalization for system F, which is not possible to prove without impredicativity. So in practice, different proof assistants have adopted different stances with regards to impredicativity. On the one hand, we have the Coq proof assistant and Lean, which have both decided to have an impredicative sort of propositions. And on the other hand, we have the Agda proof assistant, which decided to be fully predicative. And this has some consequences in terms of logical strength. Coq, like, and Lean, because of impredicativity, have a super high logical strength. So if we, I don't know, pit Agda and Coq in some duel of logical strength, well, even though Agda has some super cool features that are not supported by Coq, such as inductive recursive definitions, Coq will end up winning just because of impredicative propositions. Right. So, well, this raises a very natural question. Why is Agda reluctant to support impredicativity? Well, there are probably many good answers to that question, but possibly a very good reason is that adding an impredicative sort to a system makes it much harder to understand, and in particular, much harder to build models for, because as PL people, this is how we understand things. And there are several reasons for that. One of them is that there seems to be some kind of fundamental obstacle in understanding impredicativity in terms of more primitive logical principles. And like we cannot fully model impredicativity without using impredicativity. And so we cannot do as we do for predicative systems in like first building the interpretation of the lowest universe, and then on top of this, adding the interpretation of the next universe, and so on and so forth, because we have some sort of interplay between the small stuff and the large stuff. Impredicative propositions will live at the bottom of the universe hierarchy, but they can refer to stuff that lives much higher in the universe hierarchy. So we cannot do this kind of incremental construction. We have to build our model all at once. And this is very hard. And a good illustration of that is that we still, to this day, do not have a solid normalization model for the theory of the Coq proof assistant. So we kind of assume that it is normalizing, but who knows? Right. And since impredicativity is so hard to understand, it should not come as a surprise that every now and then, type theorists and users of proof assistants find out that, well, actually, impredicativity clashes with the shiny new feature that has been added to the proof assistant. So here is a handful of examples. Impredicativity plus injectivity of type constructors is inconsistent. Impredicativity plus excluded middle plus large elimination for inductive propositions is inconsistent. And an example that is particularly interesting for the purpose of this talk is that in 2019, Thierry Coquand and Andreas Abel have realized that the way that the Lean proof assistant implements the computation rule for equality actually breaks normalization of open terms if we have impredicative propositions, which Lean does. So for this reason, the type-checking algorithm of Lean is not complete. Well, it's also not complete for other reasons, but not like it prevents Lean people from doing some cool mathematics. Anyway, impredicativity is this sort of deal with the devil, because we get this super cool power and expressivity, but in exchange, we get this theory that is much harder to understand, and even every time we add some shiny new feature, we have to cross our fingers and pray that, well, it does not break. And we don't know this in advance because it's too hard to build a model for it. So, well, this is my overview of the situation, and it brings me to our first contribution, which is a new way to build normalization models for systems that have impredicative propositions with one additional constraint, which is definitional proof-irrelevance for propositions. This means that I ask for a proposition, well, if A is a proposition, I ask for any two of its proof to be definitionally equal. This kind of propositions are already commonplace in all modern proof assistants. You have the sort S-prop in Coq for strict propositions, the sort of Lean propositions, which is, Lean only has proof-irrelevant propositions. And in Agda, they have predicative proof-irrelevant propositions. So our observation is that basically we can fit these proof-irrelevant impredicative propositions in a predicative model construction in exchange for not computing, not normalizing the proofs of impredicative propositions. So when you think about it, it is only natural because, well, since we have the proof-irrelevance rule, this means that proofs of propositions cannot have any sort of computational content. So we have no use for a normal form. So basically, if you remember one thing from this talk is that if you have proof-irrelevant propositions and you want a decidable theory, you should not try to normalize them. Well, they're proofs. And so since we have the proof-irrelevance rule, this turns out to just normalizing the relevant part of the theory is enough to prove decidability of typing. Well, all right. It seems that proof-irrelevant propositions are more tractable than general impredicative propositions. But does this proof-irrelevant rule constrain us to have a system with two separate layers? One that is the layer of types, which are proof-relevant, and one layer of proof-irrelevant logic on top of it, which do not interact? Well, not quite. In fact, we can add some support for large elimination principles for some propositions. And the two fundamental examples are the false proposition and the equality. The false proposition is not too surprising. Basically, this is saying that if we want to prune some branch in a computation, it suffices to derive a contradiction in the proof-irrelevant layer. So really, the contradiction plays no computational role. It just says that this branch of the computation is useless, okay? And we do not have to inhabit it with some proof-relevant stuff. The equality proposition is a bit more difficult because in particular, it implies that our theory satisfies a strong version of the principle of uniqueness of identity proofs, which is the principle that Lean tried to implement, but ended up breaking normalization of open terms. So how should we support large elimination for the equality? Well, we need a computation rule of some sort. And this means that we have to find a way or another to realize this transport operation that takes a predicate on some type, 2 points in the type x and y, which are linked by an equality proof, and convert an element of p of x to an element of p of y. So how should we implement this? Well, the standard way, like for instance in Coq, is to look at the equality proof and normalize it until it happens to be a proof by reflexivity, in which case we can just simplify everything. But we cannot do that anymore because, well, E is now irrelevant. So we cannot expect that looking at E and just reducing when E is reflexivity gives anything that remains consistent. It will be very bad. So we cannot do that. We have to find another way. And the way that has been chosen by Lean is to instead look at the two endpoints of the equality, x and y. So the way Lean computes with the eliminator for equality is to normalize x and y and then try to check whether they are convertible or not. And in case they are, well, the proof of equality has to be a proof by reflexivity from proof-irrelevance, and then we can simplify stuff. And somehow Abel and Coquand used that rule to produce a non-normalizing term. But the important thing is that the Lean implementers did not respect our fundamental principle. Do not try to normalize irrelevant stuff. And the key thing is that the counterexample of Abel and Coquand is irrelevant. So if we don't try to normalize it, well, there is no reason to expect that this will fail. We did not do a proof of that because we are more interested in a second option, which is instead of inspecting x and y, to inspect the predicate p, or more precisely, the value of p of x and the value of p of y. If we reason on p of x and p of y instead of reasoning on e, we are basically implementing our transport rule via a typecasting operator. And this is exactly how observational type theory works. Observational type theory of McBride, Altenkirch, and Sweestra. And so can we prove normalization for an impredicative version of OTT with what we know now? Well, there seems to be some kind of difficulty because modeling OTT generally relies on an inductive description of the universe, which is very predicative. But with our new method, it turns out that it is actually possible to do that because we used a predicative construction to model impredicativity. So we obtain our second contribution, which is a formal proof of normalization, canonicity, and decidability of conversion for a version of observational type theory, which is impredicative. And our system not only supports all the cool new stuff that comes with observational type theory, such as function extensionality or quotient types, but also well, large elimination for false equality and all non-recursive impredicative propositions. However, there is a small caveat on which I will end this talk, which is that our system does not support elimination for the accessibility predicate, which is a specific inductive proposition. And thus, as a consequence, we have some sort of system that is in between predicativity and impredicativity, in that it has the computational expressivity of predicative theories, in that every function that you will be able to define in impredicativity observational type theory can also be defined in Martinov type theory. But however, it has the logical power of impredicativity, and you can prove normalization of system F, for instance. All right, well, thank you for listening.
All right, questions. Okay, I see Bob having raised his hand. And just remember, always state who you are, where you're from, so everybody knows.
Hi. I haven't read your paper, so my question could very well be stupid, but can I ask it anyway?
Sure.
If you don't prove normalization at all, like if you could have a divergent proposition, a proof of a proposition, then I could have a divergent proof of false, then I have an inconsistency, and you could do false elim, from what I understood. So I'm confused, like, how does that all work?
Exactly. So you do not normalize proof of propositions, but you normalize the proof-relevant part, of course. And if you are in a consistent context, there is no way you can do this kind of non-terminating proof of false. The only way you can have them is in an inconsistent context, and in which case it's not really a problem. Since your context is inconsistent in the first place, well, you could prove false, and it's not a problem that they are non-terminating because you do not evaluate them.
But I'm missing how you know this.
Just because of the sort.
I mean, if the context is blatantly inconsistent, I understand your point. But how do I know that some empty context, for example, I don't have a diversion proof of false? I'm just tripping up on a basic fact.
Right, so if it turns out that, well, piano arithmetic is inconsistent, then sure, if it turns out that arithmetic is inconsistent, then sure you can do a proof of false in the empty context. And then, but like everything falls apart in mathematics altogether, so.
Maybe you can discuss it offline.
There seems to be something unclear. Maybe we can discuss offline.
Andy Pitts.
Andy Pitts, University of Cambridge. Can you say something about the axiom of unique choice? Is it provable in your system, or is it relatively consistent with the system?
Right. So you have when you have impredicative. When you have a logic layer and a computational layer, you can do two sort of versions of unique choice. One that is uniquely logical, and that one is consistent. You can add it, but you will not extract any computational content from it. And one that is computational, and that one, well, if you add it, you cannot expect normalization of open terms anymore.
Unfortunately, it's the first one I want, so that's fine.
Okay, there's one more question. Vanil?
Hi, Neil Krishnaswamy from the University of Cambridge. Could you go back to your previous slide where you talk about the strength, that one? So this theorem, I think I'm somewhat confused by the English here. So if you prove that system F normalizes using impredicative ought, then presumably you have an evaluator for it, which wouldn't...
So no, it's only a proof in the logical layer. It's not an evaluator. You cannot extract. So in this system, you have a difference between functional relations and integer functions.
Okay. So I think this also was the answer to Andy's question.
All right. So with this, thank you so much, and we can all go to a break.